Hello everyone and welcome to today's lecture on triple integration in rectangular coordinates and in non-rectangular coordinates. So today what we're going to talk about is how to compute the triple integral. So in general, the triple integral with rectangular coordinates is the easiest type of integral to evaluate. With a rectangular domain. So we've talked about how in the last class, if we have a given triple integral over some rectangular domain, we can denote this as saying the x goes from, say, we'll go 1 to 4. This is an example. The y coordinate maybe goes from 2 to 3. And say the z coordinate goes from z to 1, or from 0 to 1. So if this is the region that we're integrating over, we can always kind of draw a picture of this. Right, this region is going, say, from 1 to 4 in x, from 2 to 3, this is 1, 2, 3 in y, and from, this is just 0 to 1 in z. So it's going to look like, in general, integrating over some region omega that looks like this. A rectangular region in 3D. So the notation for this is we say that we have a triple integral of some function. Just for example, we'll take the function x squared plus y squared plus z squared. So the triple integral of this function over this region omega is the same thing as the iterated integral for x from 1 to 4, y from 2 to 3, and z from 0 to 1 of the function x squared plus y squared plus z squared. And dv is just dx dy dz, or dz dy dx. So to evaluate something like this, this is saying find the accumulation of this function over this region omega, this rectangular region omega. And just like for double integrals, this evaluation is going to be done by doing the inner integral first, and then the outer integral, and then the middle integral, and the most out integral. And you can also see this if you kind of go through and take this integral, it becomes the integral from 1 to 4 in x, from 2 to 3 in y, and the antiderivative of x squared plus y squared plus z squared with respect to z is x squared times z plus y squared times z plus z cubed over 3. This is going to be evaluated for z from 1 to 0. So when we plug in for our z integral, we end up getting that it's the integral for, again, x from 1 to 4, y from 2 to 3. Then plugging in for z will give us x squared times 1, just x squared, plus y squared times 1, plus, and then we plug in for z into z cubed over 3, it's 1/3. It's 1 cubed over 3. And to finish the calculation, you'd go through and do the double integral of this function right here. Function x squared plus y squared plus 1/3. So really the idea of triple integral or triple integration is the same idea in some sense as a double integral. We have to, essentially determine the bounds for a region and go through and evaluate each individual iterated integral to get the final value of the integral. And we're also seeing that the triple integral of this function x squared plus y squared plus z squared is the same thing as the double integral, right, of this function right here, where this is the integral from 0 to 1 of this function with respect to z. So we're also seeing that a lot of times in general when we do the triple integral, it's really the same thing as the double integral over some region R of some function. In this case it's x squared plus y squared plus z plus 1/3, which is the same thing as the antiderivative of this function right here with respect to z from 0 to 1. So a big question that you should probably be thinking of is what happens when this region is a non-rectangular domain. Because just like for double integrals, it's a little bit different. We go to integrate over a non-rectangular domain. For rectangular domains, we have Fubini's theorem. So, and we'll also have Fubini's theorem, just like in 2D, we have Fubini's theorem for non-rectangular domains as well. But you have to be more careful when you're evaluating the bounds of integration. For a rectangular domain, you can evaluate this integral in any order that you want, dy, dz dx, dz dx dy, because the dv, or the volume element, can be expressed as dz dy dx, or as dy dz dx, and so on and so forth. We actually have 6 possible combinations of orders of integration that we can do for a function of 3 variables. So it turns out that Fubini's theorem, just like for a double integral, it also holds for triple integrals. We can integrate in any order that we want, but in general we have to be very, very careful about what order we choose to integrate in. Because if you choose a given order of integration, that necessarily means that you have to determine the bounds of integration for the chosen order of integration. So what I'll use for the example of this is the triple integral over non-rectangular regions. And we'll use actually as a homework example, the first web work problem of homework 5. So this asks you to not even evaluate the triple integral, but just to set up the bounds for a triple integral of some function over the region E, where E is the solid bounded by the surfaces z equals 0, z equals y, and x squared is equal to 9 minus y. Again, you might have different surfaces for your region E, but all of the web work problems are all the similar shape to this. And the idea is that we want to figure out the correct way of figuring out the bounds of integration for this example. This example is web work 5, problem 1. So this is a good example for a number of different reasons, but the main reason is that it gives us, in some sense, a picture of, in general, for a given region, how to figure out the correct bounds of integration for that region. And the key idea here is always going to be to look at the traces of the region in each individual coordinate direction. So you want to say, look at what the surface, or what the shape, the solid looks like if you look at the surface along the x-axis, along the y-axis, and along the z-axis. So in general, for a given triple integral problem, we're going to have 3 traces that we have to look at when we're determining the bounds of integration. The first trace is going to be along the z-axis. If you kind of look along the z-axis, you're going to see the xy plane. If you look along the x-axis, you're going to see the yz plane. And if you look along the y-axis, you're going to see the xz plane. And the idea is always to determine what the curves of the boundaries look like, the boundary of this shape in 3D. In this case, the boundary of E looks like along each one of these coordinate directions, what the traces in some sense look like if you look at the boundary of E along each one of these directions. So sure enough, if we look at E along the z-axis, right, the only equation that is really governing the relationship between x and y is this curve x squared minus 9, or equals 9 minus y, so this one right here. And the curve x squared equals 9 minus y is the same curve as the curve y is equal to 9 minus x squared, which is a parabola that's opening down and intersecting the x-axis at -3 and +3, and the y-axis at 9 right here. So if you were to look at this solid directly from the z-axis or along the z-axis, this is the picture that you would see. Likewise, we want to kind of look at what it looks like along the x-axis, or in the zy plane. And the relationship between z and y is given by these two equations right here. That z equals 0. That's the first big boundary equation, so z equals 0. And the second boundary equation is that z equals y, which is exactly a line in the zy plane. But we know that the maximum value of y in our domain is 9 because of these conditions right here. So we have to kind of draw a fixed line at y equals 9. And that gives us this right here as our region, or our trace of what we'll see if we look along the x-axis. So the last thing we want to look at is, what we see if we look along the y-axis, which is exactly going to be given by these two equations right here, the second and third equations. So z equals y and x squared equals 9 minus y. So if z equals y and x squared equals 9 minus y, then we also have that x squared is equal to 9 minus z. So we see the curve z is equal to 9 minus x squared when we look along the y-axis, which is exactly, again, going to be given by the same parabola right here, because we have z equals 9 minus x squared. Now you may have different coefficient numbers for your problem, so you might have to have a different curve than along the z-axis, but the idea is for us, we actually in this example have the same curve. It's just negative 3 to 3. X goes from negative 3 to 3, and y goes from 0 to 9, or z goes from 0 to 9 minus x squared. So using these three traces and the relationship between them, we can go through and actually develop a picture of what this is going to look like in 3D. In 3D, this surface is going to look like the following. We'll call this the x-axis, this the y-axis, and this the z-axis. We know that this right here, if we look directly along the z-axis, we're going to see this shape right here. So in the xy plane, we have that if this is 9, y equals 9, and this is x equals negative 3 and x equals positive 3. Oops, let me go a little bit closer there. This is the curve that we're getting. From this cross section right here. We know that at y equals 9, z is also equal to 9 because of the equation z equals y. And so we get exactly this shape right here when we look at the cross section in the zy plane. And this last curve right here is actually the intersection of the surface z equals y and x squared equals y minus 9, which looks exactly like the following curve. So it's starting here and kind of going up and down, so I want to make it nice. This kind of parabolic curve right here, which is exactly the shape of, looks kind of like a wedge or a doorstop. So this is all of the volume kind of contained inside here is our region E. The idea is that we only really need these three traces to determine the ultimate bounds for the final integral that we end up calculating, the triple integral. So if we call this triple integral I, the problem 1 of web work 5 asks us to go through and figure out what these bounds are going to be for a given order of integration. So for instance, if we do, we'll say the triple integral of the function f of x, y, z in the order dz, dy, dx, we have to look at the plane, or the trace, for the outer two most variables, in this case dy, dx, and ask ourselves, how is y changing with respect to x? So in this region, x is going from -3 to 3. And as x goes from -3 to 3, y goes from a lower bound of 0 to an upper bound of this curve right here, which is 9 minus x squared. And then we have to rely on this third trace, our last trace, the last two traces you can think of in terms of finding the z-bounds, the correct z-bounds. But the main idea is that it's always based off of this surface. So in this case, we're looking at how z changes with respect to y. And we see that z starts at a lower bound of 0 and ends right here on the plane z equals y. So z goes from 0 to z equals y. And this would be the correct way of drawing out the bounds for this triple integral in this order right here, dz, dy, dx. If we were to switch this order, I wanted to switch the order in some sense, so go, instead of dz, dy, dx, maybe do the triple integral of the function. We'll just do dy, dz, dx. Then we have to re-go up and we have to look at our traces and see how our variables are changing with respect to each other, so each other coordinate. So in this case, we have to look at the trace in the zx plane. So along the y-axis, and we see that, well, in this case, x is going from -3 to 3. And we also have that in this plane, y or z is going from 0 to the curve 9 minus x squared. So 0 to 9 minus x squared. So in this case, the x bounds and the z bounds stay similar to before, but again, you may have different numbers for your problem, so this trace might be a little bit different. And the last thing we need to ask is, as we move around in the zx plane, where is y going from, and where is what's the lower bound in y and the upper bound in y? Okay, so from the picture, as we kind of move around in this plane right here, the lower bound for y is going to be this, the plane z equals y, or like this right here. And the upper bound in y is going to be whatever the back surface is. So in this case, the surface given by x squared equals 9 minus y. So the lower bound for y is the plane z equals y, which is the same thing as y equals z, or y is equal to z for our lower bound. And our upper bound is exactly the parabola, or really it's a parabolic cylinder given by y equals 9 minus x squared. So this is going to be 9 minus x squared. And you can hopefully see that in order to get the correct bounds of integration for a given triple integral, you have to be very careful and make sure to draw these traces and think about what the shape looks like in 3D. Because essentially each one of these bounds is a function of the other two. So the innermost bounds in this case, the z bounds in this order of integration, z depends on x. So this is a function of x right here. These two bounds are in general functions of x. And then because our innermost integral is in y, these can be functions of both z or x, which are our outer integrals, the outer variables. So this problem has you go through and get the triple integral in each separate order of integration. And the idea is that you want to kind of use this method that I've shown to get each individual order of integration, the correct bounds for that specific order of integration. The next big integration technique that I want to talk about today is the idea of switching to a new coordinate system. Because a lot of times our region omega that we're integrating over has some sort of symmetry that's a nice geometric symmetry that we can exploit when evaluating the triple integral. So to do this, what we're going to do is recall 2D coordinate transformations. So coordinate transformations in 2D. And in 2D, if x is a function of new coordinates u and v, and y is also a function of the new coordinates u and v, so say y is equal to y of u and v, you'll remember that in order to do the integral in this new coordinate system, the integral of some function f of xy over some region R transforms in that the bounds of the region R in this new coordinate system are going to be different. So we're going to have to describe R in terms of the new bounds of integration u and v. We have to plug in the new coordinates as a function of our, or the old coordinates as a function of our new coordinates. It becomes f of uv and y of uv. And the last thing, where in Cartesian coordinates, dA is dx dy or dy dx. In our new coordinate system, it's going to actually be a little bit different. We have to multiply by the Jacobian matrix, the absolute value of the Jacobian matrix, of the new coordinate transformation. It's the absolute value of the determinant of the Jacobian matrix J du dv. And this was the correct way that we found to convert any double integral. And let's get all of this, kind of shift all this over so we have a little bit more room in terms of a new coordinate system u and v. Remember that the Jacobian matrix for a coordinate transformation in 2D is just a matrix, a 2 by 2 matrix of partial derivatives of the coordinate transformation. So all the first partial derivatives of both of these functions, dx du, dx dv, dy du, dy dv. And the determinant for a 2 by 2 matrix we calculate as the product of the diagonals minus the product of the off diagonals. So the determinant of J is dx du dy dv minus dy du dx dv. So for a general coordinate transformation in 2D, this is how we go through and go to a new coordinate system, and specifically how we translate the double integral of a function into a new coordinate system. It turns out that for a coordinate transformation in 3D, this is exactly the exact same procedure that we have to follow. Specifically, right, if we have a coordinate transformation in 3D, in general, we're going to have three new coordinates. We'll say x, y, and z are going to be equal to functions of the new coordinates. We'll call the new coordinates in general u, v, and w. So x is a function of u, v, and w. Y is a function of u, v, and w. And z is a function of u, v, and w. And for essentially the same reasons as in 2D, right, any double or any triple integral in this case, so a triple integral over some region omega of a function f of x, y, z dv is going to be equal to the triple integral over the same region. Remember, we always have to re-express that region, though, in terms of our new coordinate system in the coordinate transformation. But it's a function of x of u, v, w, which is x at our new coordinate, y of u, v, w, which is y at the new coordinate, and z of u, v, w, which is z at the new coordinate. So saying that we have to plug in our new coordinate system in for x, y, and z, and the dv for almost the exact same reason as in a double integral is going to become the absolute value of the determinant of the Jacobian matrix in this new coordinate system multiplied by dw, dv, du. So the big change, or the big change in going from Cartesian coordinates into a new coordinate system, is that the dv, the volume element, as it's sometimes called, goes from dz, dy, dx to the determinant of the Jacobian, an absolute value, times dw, dv, du. And it's very, very important that we remember this when we're translating into a new coordinate system. If you don't make this change, the volume of the small boxes in the Riemann sum process are not going to be changed accordingly and correctly in the coordinate transformation. So you have to multiply by this absolute value of the determinant of j. And so we have a little bit of a problem here. It's not a big problem, but the small problem is that we have to go through and remember what the determinant of a 3x3 matrix is. Because in general, a coordinate transformation of 3 variables is going to give you a Jacobian matrix with 3 components: dx, du, dx, dv, and dx, dw, dy, du, dy, dv, dy, dw, and dz, du, dz, dv, and dz, dw. So just like before, the Jacobian matrix is the matrix of partial derivatives, or first partial derivatives, for the coordinate transformation, and it gives us all of the first order rate of change information that we need to know about our coordinate transformation. So the idea is that in order to calculate this Jacobian determinant term, we have to be able to go through and actually calculate the determinant of a 3x3 matrix. So for some people, hopefully most people, the determinant of a 3x3 matrix was discussed in their Calc 3 course, but even if it wasn't, I'll go over how to calculate this determinant right now so you can kind of see if in general we have some 3x3 matrix, we'll call it J, and the matrix has components A, B, C, D, E, F, and G, H, I, or these are all just constant real numbers. The determinant of J can be found by what's called a cofactor expansion. The main idea is that you choose a row or a column of the matrix. And what's nice about the cofactor expansion is that it doesn't care about what row or column you choose. You can do a cofactor expansion along any of the rows or any of the columns, and as long as you follow the same procedure, you'll get the same result for the determinant. So typically what we'll do is as long as the matrix is we'll just choose this first row right here. So we'll choose this first row for our cofactor expansion. And the main idea with the cofactor expansion is that you have to consider every single element in the row or column that you choose and multiply by the determinant of all of the other things that you get when you cross out the row and the column corresponding to a given element. So this is a little bit easier to show than to do. So we'll just kind of go through and say this is going to be A times the determinant of the matrix E, F, H, I, which is what's left over when we kind of take this element A and cross off everything else in this row and everything else in this column. And then we also have to add to this the next term in the determinant, which is negative B. The next term in this row is B. And we cross off everything here and everything here. There's B times the determinant of what's left over. which is D, F, G, and I. And lastly, we have to add to that the last term in this cofactor expansion, which is C times the determinant of what's left over when we cross out everything not in this row or in the column corresponding to C. So it's C times the determinant of D, E, G, H. And you can go through and then calculate the final value here by looking at, well, this is A times the determinant of this 2 by 2 matrix, which is E times I minus F times H minus B times the determinant of this 2 by 2 matrix, which is DI minus GF plus C times the determinant of this 2 by 2 matrix, which is DH minus GE. And in general, this is the way of going through and calculating the determinant of a 2 by 2 matrix, or of a not 2 by 2, but a 3 by 3 matrix. You have to go through and evaluate this expansion. This algorithm, by the way, applies not just to 3 by 3, but to any higher matrix, so a 4 by 4 matrix or a 5 by 5 matrix. But for this class, we're only going to be considering 3 by 3 matrices because this is all we need to get the correct expansion for the determinant of the Jacobian matrix for a given coordinate system in 3D. So let's go through and see some examples of new coordinate systems in 3D. The first example is what's called cylindrical coordinates. Which is very similar to and almost the same thing as polar coordinates that we already know in 2D. It's the transformation x is equal to r cosine theta, y is equal to r sine theta, and z is just equal to z. So the Cartesian coordinate z stays the same. And the idea, the reason it's called cylindrical coordinates is that it's based on cylinders, varying cylinders of radius r, which essentially all describe every single point in three-dimensional space. So the most important part of the coordinate transformation is always that the dv in your new coordinate system, in this case cylindrical coordinates, is going to be the absolute value of the determinant of the Jacobian matrix times the differentials for each individual coordinate direction. So in this case, dz, dr, d theta. And we need to figure out what the absolute value of the determinant of the Jacobian matrix is going to be in this case. And if you remember what we did for polar coordinates, it shouldn't surprise you that the result that we're going to get is that dv is r dz dr d theta. So we'll show this right now. I'll kind of go through and show how this is why this is the case. So the Jacobian matrix is dx dr, or partial x partial r, which is cosine theta. It's partial x partial theta, which is negative r sine theta. It's partial x, partial z, which is 0. And then the next row is partial y, partial r, which is sine theta. Partial y, partial theta, which is r cosine theta. It's just all the partial derivatives of x, y, and z with respect to r, theta, and z. And then partial y, partial z is 0. Then partial z, partial x is 0. Partial z, partial y is 0. There's a partial z, partial r is 0. Partial z, partial theta is 0. And partial z is 1. So if we use our Jacobian determinant formula, this becomes cosine. The easiest row to do a cofactor expansion on is this last row. But I'll go through and use the general formula that I showed before to show that really the cofactor expansion will give you the same result no matter what row or column you choose. So from that previous formula, this is cosine theta times the absolute value, or the determinant of r cosine theta, 0, 0, 1, minus negative r sine theta times the determinant of what's left over when we cross this out. So it's sine theta 0, 0, 1, and then lastly plus 0 times the determinant of sine theta negative r cosine theta. So I'll make a little bit more room here. That's 0 times sine theta r cosine theta 0, 0. And this is 0, this is 0, so this entire term goes to 0. And what we're left with is cosine theta times r cosine theta times 1 minus 0 plus r sine theta times sine theta times 1 minus 0. Which is equal to r cosine squared of theta plus r sine squared of theta, which if we factor out r is the same thing as r times 1, just equal to r. So the determinant of the Jacobian for cylindrical coordinates is equal to r, which means that this justifies what we thought before, exactly what we thought before, that the dv, the new dv in cylindrical coordinates or cylindrical polar coordinates is r dz dr d theta. So this is in some sense showing that we're exactly on the right track with our coordinate transformation. We're getting exactly what we expect from the coordinate transformation. So the next coordinate system and the other, like we'll say, main coordinate system from this class that we'll be finding very useful is what's called cylindrical coordinates. It's another good example of a coordinate system. Or not cylindrical coordinates, but spherical coordinates. We just did cylindrical coordinates. And typically, there's a number of different notations for spherical coordinates, but what we're going to do is we use the symbols rho, theta, and phi for spherical coordinates. So the idea here is that we want to be able to describe points in three-dimensional space with Cartesian coordinates x, y, and z in terms of these new spherical coordinates, which we call rho, theta, and phi, where rho is the distance, direct distance from the origin, or the radius of a sphere from the origin to any point. Theta is the angle from the x-axis, the normal angle that you typically think about when you do cylindrical coordinates. And phi is a new angle. It's the angle from the y-axis, or from the z-axis. Sorry. So let's get a picture here to kind of see what these new coordinates are going to be. So let's say we have an x-axis, a y-axis, and a z-axis. We have some point in three-dimensional space, x, y, z. So rho is the exact distance out to that point. So this is what we call rho. You can also think of rho as the magnitude of the vector going out to that point in 3D space. Phi we call the angle from the z-axis that goes down to that point. So I think of this as the following angle. It's the angle, sometimes it's called the angle subtended by the point from the z-axis, or away from the z-axis. And this is enough information to directly determine, right, exactly what the value of the z-coordinate of this point is. So if you have a given point and you look at the z-coordinate of this point, and you want to figure out how the z-coordinate depends on rho, the distance out to the point. So let me make it clear that rho here is this distance. It's the distance of the line from the origin out to the point. And if you draw a line straight, right back to the z-axis, which gives us the z-coordinate of this point x, y, z, you'll notice that no matter what point you choose, you always get a right triangle. When you look at the comparison between the distance of the vector that goes out to the point and the height of the point, or the z-axis or z-coordinate of that point. So because this is a big right triangle, this is the same thing, right, as and we can use all of our trigonometry. So say you look at sine of phi or cosine of phi. We'll look at cosine of phi first, because that's what gives us our z coordinate. Cosine of phi is the adjacent over the hypotenuse, so it's z over phi. Sorry, z over rho. So if we solve this equation for z, we get exactly that z is equal to rho cosine phi. And this is exactly what z is in spherical coordinates. It's the distance out to the point multiplied by cosine of the angle subtended by the z-axis. We can do this exact same procedure in the other direction using the opposite trig identity. So if you call the distance from the z-axis to this point r, you know that the point down here in the xy plane intersects at some point. If this distance is r, then this distance is also r right here. So what we want to do is figure out an expression for the x coordinate of the point and the y coordinate of the point as well. And we said that theta is the angle from the x-axis. And again, we have a right triangle right here. So using our normal cylindrical relations, x is equal to r cosine theta and y is equal to r sine theta. But we know that r, we use this as our r, is related to rho and phi in a very specific way. Sine of phi is equal to r over rho. So r, the radius of the out to the point in the xy plane, is going to be r, which is rho times sine phi. So this r for x is actually equal to rho times sine of phi times cosine of phi, or cosine of theta. And this r right here is, again, it's rho sine phi times sine of theta. So our x coordinate in spherical coordinates is rho cosine theta times sine phi, and our y coordinate is rho sine theta sine phi. And this gives us a complete description of any point x, y, z in terms of the distance out to the point rho, the angle theta, which is the angle to the point from the x-axis, and the angle phi, which is the angle subtended from the z-axis, or down from the z-axis. And the reason, for the name spherical coordinates is, again, because any point is a point on a sphere of radius rho. And we can directly verify that. If you don't believe that, you take x squared plus y squared plus z squared, which is I need a little bit more space here, so the same thing as rho cosine theta sine phi squared plus rho sine theta sine phi squared plus rho cosine phi squared. This is the same thing as rho squared times cosine squared theta sine squared phi plus sine squared theta sine squared phi plus cosine squared phi, which is the same thing as rho squared cosine squared theta plus sine squared theta times sine squared phi plus cosine squared phi, where we know that cosine squared plus sine squared is 1. So this is rho squared times sine squared phi plus cosine squared phi. And for any angle phi, sine squared phi plus cosine squared phi is also just equal to 1. So this is equal to rho squared. And what we've shown is that spherical coordinates is exactly just equivalent to talking about the coordinate of a point xyz on a sphere of radius rho. X squared plus y squared plus z squared is in fact equal to rho squared. So this is pretty cool. This gives us a different description of points in three-dimensional space than Cartesian coordinates. And it's also different than cylindrical coordinates. It's a little bit more complicated, but it very, very much greatly simplifies any integral that is expressed on either a spherical domain or any integral that has a function which is spherically symmetric. So the last thing that we want to do is figure out what exactly the volume element, or the dV, is in spherical coordinates. So from our general coordinate transformation rule, dV is going to be the absolute value of the determinant of the 3×3 Jacobian matrix for this coordinate transformation times d rho d theta d phi. So what we have to do is go through and compute this, and it's not the same thing as cylindrical coordinates, a different coordinate transformation. Therefore, this determinant is going to be different. Turns out that this is exactly equal to rho squared times sine of phi d rho d theta d phi. So if you want to use spherical coordinates, this is the correct Jacobian to use, the determinant of the Jacobian matrix. And what I'll do for the final part of this lecture is go through and actually show this. It's a little bit of a long computation, but it's not too bad. The main idea being that we have to calculate the Jacobian matrix and then take the determinant of that 3×3 matrix. So what's the Jacobian matrix for this transformation? It's exactly going to be dx, d rho, dx, d theta dx d phi dy d rho dy d theta dy d phi and dz d rho dz d theta and dz d phi. And I'll kind of take the spherical coordinate transformation and kind of bring it down here so that we can see what the partial derivatives are for each individual function. So our coordinate transformation is given by these three functions for x, for y, and for z. So to calculate the Jacobian matrix, J is going to be dx d rho, the partial derivative of x with respect to rho, which is cosine of theta times sine of phi, dx d theta, which is going to be negative rho sine of theta sine of phi, and then dx d phi, which is going to be rho cosine of theta times cosine of phi. Next, we got to do the next row, which is dy d rho, or sine of theta times sine of phi, dy d theta, which is rho cosine theta sine of phi, and dy d phi, which is rho sine of theta cosine of phi. And then for the last row of this matrix, it'll be dz d rho, which is cosine of phi, dz d theta, which is 0, and then lastly dz d phi, which is negative rho sine of phi. Now you can definitely go through and do the formula using a cofactor expansion of the determinant to figure out the determinant of J. You can use the first row if you want to, but for this matrix right here, the easiest row to choose is the last row, because this last row has a 0 in it, which is much simpler than the other two rows. It's going to simplify our calculations a lot. I do encourage you to go through using any row you want. Use the first row, the second row, or any of the other rows to determine the determinant of this 3x3 matrix. But the nice thing about that cofactor expansion that I talked about before is that it doesn't care about the row or the column that you choose, as long as you're consistent with how you apply the formula. So what we're going to do is do a cofactor expansion in the last row. Because we have a 0 in this last row, which is going to simplify our calculations. So this is going to be cosine of phi times, we cross out this column and this row right here, so it's times negative rho sine theta sine phi and we also have then rho cosine theta cosine phi, rho cosine theta sine phi, and rho sine theta cosine phi. So it's this, and it'll be minus 0 times the determinant of what we get when we cross out this row right here in this column right here. But I'm not even going to fill this matrix out because it turns out that it's being multiplied by 0, so this term is going to be 0. And then lastly we have to do plus negative rho sine of phi times the determinant of what we get when we cross out the row and the column associated with this last entry. So what's left over is exactly cosine theta sine phi negative rho. Need a little bit more room here. I'll take this and pull this over a little bit. Negative rho sine theta sine phi sine theta sine phi rho cosine theta sine phi. And you can already see how choosing the correct row for a cofactor expansion is sometimes very, very important, because if we chose the first row, say for a cofactor expansion, you'd have to go through and get each individual term, even though everything would simplify very nicely at the very end of the calculation. So this first term is the same thing as cosine of phi times, then it's the determinant of this matrix. So it's this times this, which is rho squared sine squared of theta sine of phi times cosine of phi. This is times negative 1 as well, because you have a negative 1 right here. So it's this times this minus rho squared cosine squared of theta. It's this entire thing times this entire thing sine phi cosine of phi. That'll be minus rho sine of phi times this, which is rho cosine squared theta times sine squared of phi. So it's this entire thing right here times this entire thing right here minus, you have a negative right here, so minus negative is a positive. This rho sine squared of theta sine squared of phi. which is the same thing. We can kind of do a little bit of factoring out. If we factor out a row from this addition right here, you have a row right here, so you have a row squared. So this entire thing is just going to be equal to the row squared. And you can also factor out a sine of phi from here, and from here. So it becomes, actually, we'll do rho squared sine of phi multiplied by and what's left over when we do that factoring is going to be negative rho squared sine squared of theta from this term right here times cosine of phi, but you also have a cosine of phi right here. So it's minus rho squared cosine squared theta all of this times cosine of phi. And you have a cosine of phi here, so this distributes to this. It's this term and this term, so it's cosine squared phi. And then in this parentheses, we then also have this term right here, which we factored out, rho squared sine phi. So what we have left over is minus cosine squared theta times sine squared of phi minus sine squared of theta times sine squared of phi. So we can also factor out from this negative 1. This is the same thing as negative rho squared sine of phi times, and I just realized that I factored out this rho squared, so this is not an issue, and this is also not an issue. And you can hopefully see that this clears up a lot. So this is sine squared of theta plus cosine squared of theta times cosine squared of phi plus cosine squared of theta plus sine squared of theta times sine squared of phi. And immediately we can say, well, sine squared plus cosine squared of any angle is 1. This is also 1 because it's cosine squared theta plus sine squared theta. So this is equal to negative rho squared sine of phi times cosine squared of phi plus sine squared of phi, which itself is also equal to 1. So the determinant of the Jacobian matrix for this coordinate transformation is just negative rho squared sine of phi, which means that our dv for this coordinate transformation is going to be the absolute value of the determinant of the Jacobian matrix, d rho d theta d phi, which is the absolute value of negative rho squared sine of phi d rho d theta d phi, or just rho squared sine of phi d rho d theta d phi. And this is how we justify the Jacobian determinant term and the volume transformation term in a given triple integral. This is the reason why. So for the next homework, for homework 5, there'll be a number of integrals which you can only really get analytically by switching to either cylindrical or spherical coordinates for the easiest coordinate system to evaluate the integral. And in order to do that correctly, you have to use this dv in the triple integral. But we'll see this next class. I'll go over a couple different examples of how to use this when evaluating a triple integral in spherical polar coordinates, it's called. Thank you very much for tuning into the lecture today, and I hope you have a great day.